Hello students, the topic for today is the transformer, right? We are beginning with the article of a transformer. Now, what is a transformer? It is supposed to be a device which is used for many purposes, right? So what is basically to define a transformer? A transformer is said to be a device which can step up or step down, that is step down, alternating voltage or current. That is supposed to be the basic behavior or basic definition of a transformer. It is an essential AC device. It does not work on DC, right? It does not work upon DC. It's basically an essential AC device, correct? Now, what is the idea behind the transformer? That is to step up and step down the voltage. And you can see these devices everywhere. You can see the devices at the corner of your neighborhood, on the poles somewhere at the corner. And there are miniature transformers also, and there are very large transformers also. They are a part of almost everything which we use electronically, because we do require the voltages to be stepped up and stepped down. Now, what's the physics behind a transformer? That is supposed to be the mutual induction. So the principle behind the working of the transformer is supposed to be defined as the mutual induction. Right? That's a mutual induction. Now, what does a mutual induction basically talks about? It says whenever there is a change in the magnetic flux, or we can say there is a variation of the current in the primary, there exists an induced EMF, and additionally a current also if we have the circuit to be closed. An induced EMF or current in the secondary due to coupled inductive coils. Right, so in a nutshell, we can say that this is an idea of the mutual induction. So mutual induction is supposed to be the idea or the principle behind the working of the transformer. Right, so it is going to demand to ourselves the primary coilings and the secondary coilings. Now, there are two basic kinds of the transformers. One of them is supposed to be defined as a core type transformer, and the second is taken as a shell type transformer. Now, what is a core type transformer? It's as a metallic core is made up of soft iron. For what reasons, we will look into the article later on in the today's lecture itself. And we have these as the windings of the primary coil and these as the windings of the secondary coil. So this is supposed to be known as a core type, where the primary and the secondary coils are wound on basically the same core only, but different limbs. So you can consider this to be a left limb over here and this as a right limb. So on the different limbs of the core. And further, we can see the coils hence surround the core. right? So the core looks like surrounded by the coils everywhere. That's known as a core type transformer. And then we have the second type, that's known as shell type transformer. Now, what is there in it? It's like a shell. Now, what have we done is over here? This is the shell type. We have the windings here, like this, and windings here. It can be constructed like this inside this complete core, where we have the windings here and the windings here. Okay, so what do you see? That this is a transformation to the shell type. Now, what is the shell type? We are bringing the coils on the same limb, right? We are bringing the coils on the same limb. So they basically are wounded over each other. So the primary and the secondary coils are wounded on each other, right? And it looks like the core, which is there, is basically surrounding the coils. That's what it looks like in this. So the core surrounds the coil. That's known as a shell type, correct? So we have defined it. We have talked about the principle behind it. We have checked out what are the varieties of it. And now we need to look into the construction of it, basic construction of it, and the working of it. So the construction and the working of it, just like any other devices, we need to take care of all these aspects. The aspects are supposed to be the definition, the principle, then types of it, construction, working, equations, uses, right? That's all. Construction and working. So how do we construct it? These are some rectangular sheets. These are the rectangular sheets. These are coupled. Right? These are coupled like this, right? That forms the core of it. So that's known as a core of the transformer. And then we have the primary and the secondary coilings. So we have the primary coiling on one of the limbs. So you can understand which particular kind of the transformer I'm talking about. So I'm talking about the core type transformer here, right? So this is known as a primary coiling. And why it is known as a primary coil? Reason because it is connected to an input AC. An input AC. So that's what is the primary coiling. That's known as a input resistance, and this is your input AC. That is a V as V naught sine omega t. So that's a primary voltage over here, correct? That can be fed to it using the generated AC over there, right? So that's a primary part. What is the secondary circuit? So what's a primary circuit? A primary circuit is supposed to be the circuit which is connected to the input AC, which means the primary coil is connected to the input AC. That's the meaning of it. That's known as a primary coil. That means the energy is fed through the primary circuit. That's a feeder. That feeds the energy, correct? Now that's a primary. That's a primary circuit. And then we are dealing with the secondary. So primary is basically like an input, and the secondary is like an output. So over here we can obtain the output. So you can connect a load over here, right? Your household load. So this circuit is termed as a secondary circuit, right? A secondary circuit. Just a second. Now, so what is a secondary circuit? The circuit which consists of the secondary coil across which the output is obtained. That's defined as a secondary circuit, correct? So that's what is the basic behavior of a transformer is. So there are two parts of it. Exactly, there is three parts. The main part is the core. That's the core of the transformer. So what is the core of the transformer? That is made up of soft iron core, soft iron, right? So we have the coupled soft iron sheets on which the primary and secondary coils are wounded. It's known as a core of the transformer. Correct. So that is what is the basic of it, and that is what is the basic construction. Now, the working of it. Transformer is supposed to be one of the very efficient devices, very, very efficient devices. Now, we will see to it in the later part of this also that why it is supposed to be so efficient. But to mention out, it is a very, very efficient device, right? So the working part of it. The working is, of course, a mutual induction. So I'm constructing a diagram once again. These are your couple sheets. Right? And this is the input. If we assume that, let's say we keep the resistance in this to be on the lower side, right? So assumption is there that we have the resistance of the input as low. Right? So such that means it behaves almost like a pure L circuit. So it's an inductor. So it's supposed to be made up of the copper wires, and we can use a thick copper wires. So if we use a thick copper wires to make it, that means that we are basically dealing with the pure L circuit almost. So that means the power losses over here in the primary circuit is negligible when the current is flowing through it. So it will be like a wattless current flowing through it. So if the resistance is supposed to be very low, that means when the AC input is fed, when the AC input is fed, so the primary behaves as a near pure inductor, and therefore the current is needs. This is altogether when we are telling that there is no load connected, right? There is no load right now across the output. Right? That's the current behavior right now. So there is nothing because it is not delivering the power basically. So if it is not delivering the power, so it will not be wasted. We will not be wasting the energy, right? So there will be no input power. Electricity bill is not going to be generated. That means there is supposed to be the no power consumption over there. So no power delivered. So therefore there is no power delivered. Right? So wattless current does not deliver the power. So that's what exactly it is happening because the load is not connected since, correct? And now the load is supposed to be connected, of course, and then the things are going to work upon. So what happens exactly right now over here? So for explaining that, just assume that this is the core, correct? And these are the coilings. So forget like what kind of circuit is there right now, and just focus upon that what happens when the AC is fed, right? So when the AC input is fed. So when the AC input is fed, there is supposed to be the variation of current over here. That means IP will be there. That's a primary current that is equal to I naught sine of omega t over here. It's fed at a particular frequency. And so the polarities keeps on changing. See, this will be plus minus, and then it will keep on changing, right? It will keep on changing. And then after half cycle, it is going to become as a minus and plus, right? This will be changing, and this will become as minus and plus and so on. And so it will keep on changing. So I'm not sketching the polarities over there. Keep on changing over there. So there is a variation of current. What do we say? There is a variation of current. So there's a variation of current across the primary. Good. So that generates the magnetic field and a variation in magnetic field. So where is a magnetic field? So let's say this is the magnetic field, which is generated here in the coil. But since this is a soft iron core, so the soft iron core is highly permeable. So let's write in the theory what is happening. Due to input AC fed, there is the variation of current and hence magnetic field across the primary coil. Correct? This magnetic flux, of course, which is variable, is fed completely to the secondary circuit. Whatever was happening in the primary is now getting transferred to the secondary, and now the theory is building up. It's fed completely to the secondary circuit due to strong coupling. Right? We have a strong coupling. So how do we show that? This is like this. These magnetic field lines form the closed loops. So these field lines form the closed loops. See, this soft iron core is a ferromagnetic material. And the ferromagnetic materials are supposed to be highly permeable. What they are? They are highly permeable. That means they have the high permeability. Highly permeable. So permeability is supposed to be very high. So the mu is very high. So what happens? It does not allow the straying of the magnetic fields. So it prevents the straying of magnetic field. And that's what is known as strong coupling. Correct? That's the meaning of the strong coupling. What does the strong coupling means? That all the flux is getting exchanged. So that generates a strong coupling. If it is not a ferromagnetic material, then the field flux lines will pass here and there. There will be the stray losses, but there are no stray losses in this idea. So all the flux is going to be reaching where? Across the secondary coil, so now constructed. So that's the secondary coil. So as a construction, you can see the number of the terms which I have drawn in the secondary is different. Right now it is larger in comparison with the primary. The diagram you should note whenever you look at the diagram which is given in the question. So look at this aspect. An idea at it that what kind of the transformer you are dealing with. Right. So this is a secondary coil, and what happens? This flux reaches the secondary. So hence the variable magnetic flux across the secondary. It's a beautiful idea. We have been doing this repeatedly in the article of the electromagnetic induction. Hence, the variable magnetic flux across the secondary coil. Induces an EMF across it. So that is going to generate a EMF across there. So that means this will become positive and this is negative. Oh, then it is going to once again change. So it is going to once again change. And then in the next cycle, it is going to become as negative and this as positive. Correct. So it keeps on changing as the polarities of the input are going to change. The polarities of the output are also going to change. Correct. So this induces an EMF. So what kind of an EMF will be there? The EMF over there, that will be again the AC itself. So that will be an alternating EMF itself. Right? That's an alternating EMF across this. That's quite simple. That's quite simple. See, when you are talking about the theory in this mannerism, see this. We have the input. Let's say the input which was there as the EP or VP. Let's write VP as equal to V naught sine omega t. So what is that? IP. So that IP is equal to I naught sine omega t. V is for primary. Correct. So what is dip upon dt? That becomes I naught omega cos omega t. Okay. So like it behaves like a solenoid. So what's the value for the magnetic field? That's equal to mu naught into Ni. That is across the primary. So what is dB upon dt? That is mu naught into N into dip upon dt. Correct. So what is the variation of flux? So that's d phi upon dt across the secondary. So should be equal to dB upon dt and into the area of the secondary. So that's equal to area of the secondary and into mu naught into N into dip upon dt. And what is the dip upon dt? That is I naught omega cos omega t. That induces a EMF in this magnitude. Polarities will keep on changing. Okay. So this whole term can be written as equal to E naught cos omega t. So that generates the alternating secondary voltage. And what will be IS? Oh, that will be as equal to I naught across the secondary cos omega t. So that's what the behavior is here basically. This is how the flux is getting transferred from the primary to the secondary and the alternating voltage is getting developed across the secondary. Okay. And it is the current is going to depend upon the amount of the resistance which is there in the amount of the load which is present inside the secondary coil. Okay. So it induces an EMF, alternating EMF across it, and hence an alternating current flows across the connected load. Right, so that's how it works. That's how it works. And now what exactly happens? Listen to it. So it's quite easy to understand. What happens exactly? See this. See now when we are connecting a load across this, so load means what? A resistance. So this circuit becomes kind of an LR circuit. It becomes what? An LR circuit, right? So it becomes an LR circuit. What happens? An LR circuit is having a phase. So the secondary circuit now behaves as an LR circuit, LR series AC circuit. Therefore, there is a phase difference between the V and I depending on load. So it depends upon how much load you are connecting, and you will be having that phase. We know that, right? So that is a reactance, and this is a resistance, and that's a phase, and a tan of phi is and cos of phi is supposed to be equal to R upon Z. We do remember that. So which means higher is a load, that means R will be higher, so the cos phi will be higher, which explains that the power factor, that is cos phi, is higher. So that means the higher consumption of power, so higher power consumption. So that's quite simple. That's, of course, your electricity bill should run high. Now this phase difference which is induced. So since the power is consumed in the secondary, it sets up the phase across the primary. See, whatever is happening in the primary was delivered to the secondary, and now the secondary is also coupled with the primary. Now, what is happening in the secondary? There is a LR circuit, because of it there is a phase variation. That phase variation has to be shifted because there is 100% variation. So hence, the input circuit generates power to match up, right? To keep up with the phase variation across the keep up with the phase of the secondary. Right? The phase has been set up as per the load. See, actually what happens, we keep on shifting the load. We keep on shifting the load means sometimes in our houses, sometimes in the neighborhood, we have the higher consumption and sometimes lower consumption, like we switch off the AC, switch on the AC, switch on the geyser, switch off the geyser, and connect 2-3 lights or a couple of fans and then switch them off according to your mood, according to your usage. And therefore, there will be the load amount variation. And when there is a load amount variation, so cos phi will keep on changing. So the power consumption will keep on changing. In a day, at every instant, the power consumption is not the same, right? So what keeps on happening? What keeps on happening that a power consumption keeps on changing because the load amount which you are using or connecting to the output is keeping on changing. So there will be a variation of the phase, and the input has to keep up with that variation of the phase. So now the input develops that particular phase. That means it develops kind of a virtual resistance, right? So hence, an input resistance is kind of a virtual resistance develops, which develops what? Now there will be input resistance. That means now there will be the power delivery. Beforehand, we were talking the input was supposed to be pure inductor. So it will not deliver any power because there is supposed to be pure inductance. So cos phi will be 0. But now there is supposed to be a phase variation because of the secondary. Because the secondary was a load, so there was LR circuit. So with the phase variation, so the input and the output are coupled up. So that phase variation is supposed to be kept up by the primary also. A primary develops for that what? A virtual kind of a resistance. So it develops what? The input power. And now you have a power. See, when the output load is not connected, so why the input circuit is going to deliver the power? Now the output load is connected, and as per the requirement, as per the phase, as per the power factor, there will be the input, and so it will develop the input power. And now how efficiently that input power is going to be delivered. See, a consumer is first of all going to ask that, give me this. And then it depends upon that the supplier is going to give that with how much efficiency. So the input is like a supplier. Input is like a supplier and the output is like a consumer. So consumer first of all demands, and then the supplier basically provides that power, and now the efficiency is going to come in. So it develops the input power if the transformer is highly efficient, then most of the input power generated is transferred to the secondary, right? Secondary circuit, that is across the load basically, right? So that's what the idea is. Now the efficiency is going to come in when we are delivering the power from the input to the primary. But why secondary is asking that this much load is connected, so this much resistance is here, so this much power is required. Now you transfer the power. So coupling basically explains that there is a channel between the supplier and the consumer. So the secondary circuit, which is the consumer, basically tells that this is my demand, and the primary delivers it, and the medium in between, that is a a soft iron core, it should be highly efficient. The rest of the structure should be so much efficient. The rest of the construction should be so much efficient. That is power delivery, which is from the input to the output, is very, very efficient. And that is going to basically tag in that the transformer is supposed to be a highly efficient device. So that's what is the theory. That's what is the theory on this. Now, the whole idea comes to efficiency now, that this power is to be delivered efficiently. How to? So we say when you have a very strong coupling. So which means perfect coupling. So if there exists perfect coupling, and assuming that the load is not so high, so that's another kind of an assumption, that the load is not very high, right? And there exists a perfect coupling. Then what happens? We say the efficiency is nearly 1. But what is efficiency basically? So efficiency nears 100%, keeping all other assumptions intact, and the losses kept negligible. So there are a lot of conditions. We cannot ever say that it's 100%, but we can think about it. We can think about it if we are just keeping all the assumptions to be intact. As I said, that input, we don't have resistance applied from our side. If we apply resistance from our side, then we are already disturbing the power balance. That already there will be the internal losses. Just like we have a input battery, DC battery. So DC has an internal resistance. What will happen? There will be a power loss, definitely. So over here also, if you apply by your side a resistance in the inputs, what is going to happen? There is supposed to be power losses. So 100% efficiency cannot be met. But if you do so, that you try to reduce it by increasing the cost of construction, that is by using the thick copper coils. In that case, the resistance can be minimized to great levels. So even the 99% transformer efficiency will be very good. 97%, 95% is also excellent. Even 90% is too good. So how do we write efficiency? Efficiency is supposed to be the power output. That is the power across the secondary. Power output is across the secondary upon the power input. So that is the power across the primary. So how do we write that? How do we write that? So power is equal to what? Voltage into current. Okay, so then let's talk about the voltage. So what does a perfect coupling means? That is a flux per turn. It's not about how many turns are there. It's a flux per turn. You can have a single turn here, single turn there, a single loop, a single loop there. So whatever lines are there, they must reach the secondary across one loop of the primary to the one loop of the second. And then you can increase the number of the turns. The theory has to be for the basic quanta. So one quanta of the primary, one quanta of the secondary, and then you can increase the number of the turns in the primary or in the secondary later on. So flux per turn across the primary is equal to flux per turn across the secondary, right? So be very careful in what I have written just now. Very, very important this statement is. So the flux per turn, that is a flux across the primary upon number of turns of the primary. So that becomes flux per turn. So that means there are this coil, which has so many turns. So total flux divided by the number of turns. So that becomes the flux across the single loop. Correct? So that's the flux across the single loop of the primary is equal to flux across the single loop of the secondary. So that is a net flux across the secondary divided by the number of the turns of the secondary. We are making it sure that we are talking about each and each. And then you can grade it. Right? Then we differentiate on both the sides. So we have d phi upon dt upon np, and this is equal to d phi s upon dt and upon np, and then you can use a minus sign also on both the sides. So this is going to generate by the Lenz's law and the Faraday's law, because this idea is basically coming from EMI. So that is EP upon NP, and this is equal to ES upon NS. That becomes your relation. EP upon NP as equal to ES upon NS, correct? Now, so we can write this as ES upon EP as equal to NS upon NP. That is the number to the number of turns in the primary, number of turns across the secondary to the number of the turns across the primary. And that is supposed to be equal to NS upon NP. What is NS upon NP equal to? That's defined as K. And what is K? That's the transformation ratio. coming from the word transformer. That's a transformation ratio, the K. Right? It can be more than one, it can be less than one, depending upon how you construct and what is the desirable output. What do you want from the transformer? It's a step-up device. Step-up device for what? Voltage, current, and would you want to step up the voltage or step down the voltage? Or you increase, or you want to step up the current? What do you want? We need to check that later on. So what is the power across the secondary? We can write that is equal to EP ES and IS. That's a voltage developed across the secondary. That's a back EMF basically, which is getting developed by the Lenz's law, induced EMF, and into the secondary current as it will flow, as we have already discussed the theoretical part of it and equation part of it also. And how does the primary current basically ultimately leads to the secondary current, and divided by that is EP/IP. Oh, that's it. And so it is basically equation ES/IS as equal to eta EP/IP. That's a basic equation. That's a basic equation. You can get the numericals of the efficiency also. It's an 80% efficient device. It's a 90% efficient. So mostly you will see the numericals if you get it of the that percentage defined efficiency. You will find that the eta is around 0.9 to 0.99, something like that. Okay, so it's a very efficient device. So most of the questions are on 100% efficient device. So keeping that idea intact, that if eta is equal to 1. So if eta is equal to 1, that efficiency is 100%, my dear. Are you getting the point? 100%. 100%. So in that condition, the ES/IS is supposed to be equal to EP/IP. If it is so, which means we have the IP upon IS as equal to ES upon EP. And so this equation combined with this can be now written as NS upon NP. What is NS upon NP? The transformation ratio K is equal to ES upon EP, the ratio of the output voltage upon input voltage, and is equal to reverse, that is the input current upon the output current, or the primary current upon the secondary current. And good equation to remember. But this is when efficiency is 1. If the efficiency is not 1, then you can accordingly use it. Then you can accordingly use this, that this relation will look like ES upon EP as equal to eta times of IP upon IS. Correct. So so do remember that particular thing, and then accordingly you can use it in the relation over here, which we have developed now. Okay. So keeping the efficiency equal to 1, and now this is the relation with us, and now how to use it. So let's design it as a step-up voltage transformer. So if it is step-up voltage transformer, what do? We want ES more than EP, and that is only possible. It's only possible if we keep NS more than NP, as you can see in this equation. If NS is more than NP, so the value for the K is more than 1, and which automatically sets up that the ES upon EP is more than 1, or the voltage across the secondary is more than the primary, and you have stepped up the voltage. The same voltage which was alternating, and same voltage which is across the secondary is still alternating, but it is stepped up. If you want the other side of the coin and you want the step down voltage transformer, right? See why it does not work upon DC. Why it does not work upon DC? I will show you. Come this side. See, this whole idea from the primary to the secondary leads to this value, that is a E naught. So that E naught is AS mu naught into N I naught into omega, correct? That's a peak value across the secondary. That's the secondary peak value. Getting it? Secondary peak value. Now, if it is a DC, so in the DC, omega will be 0, and therefore the peak value will be 0. So there will be nothing obtained over there. Got a point? So this device is essentially an AC device. It can step up only AC, it cannot step up the DC. Got the point? Right? So when you get a question that the transformer does not work upon DC, so you need to answer as I answered to you. Step down voltage transformer, that means you keep the value for the K less than 1. So the number of turns in the secondary will be lesser, and therefore the input voltage will be stronger and the output will be lesser. So it's to AC passing through your main meter in your household, the main electrical meter. And now then what happens after that? So what happens? You require a charger. You require a charger, and the charger is 10, 12 volts. 10, 12 volts. If the 220 volt AC is coming inside, what will happen? Your charger is gonna burn out. Your phone may be burning out. It will burn out and blast out because there is a 220 volt and your specification is only 10 volt, 12 volt. So what do? We don't do anything. We just buy a charger which is super efficient. Means what? It has a transformer inside. It has a transformer inside which is going to step down the voltage from the 220 volt which is passing through that particular plug pin. And what you are doing, you are using a transformer in between, which is in the body of the charger. A charger is a motor like there is a transformer inside, and that is going to step down the voltage to the 10, 12 volt, which is basically required for the charging of your phone. So that's a key part which we keep on using every day in your laptops and across your refrigerators, across your TVs. It can also stabilize the voltages because it can increase or decrease the voltages. So, and you need to decide first of all that which kind of the transformer you're going to design, because once it's designed, it is going to work accordingly. That means if you are designing a step-up voltage transformer, that means a construction diagram should show like this. That is the primary, my dear, and this is the secondary. So the number of the turns are more. So that explains that's the step-up. That means if it is supposed to be, for example, a 220 volt, this might be as around 4400 volts or 44,000 volts. That's a step-up. And on the same lines, you can have a step-down transformer also, step-down. It's a step-down transformer. It's a step-down. That means maybe this is supposed to be as a 44,000 volt line, and this is reducing to, let's say, 220 volt, reducing. So it's a step-down voltage transformer. Now, we have another story which says if we want a step-up current transformer, what I'm telling, a step-up current transformer, then what to do? Then I require the IS to be more than IP. And if IS to be more than IP, then the NP is supposed to be more than NS. And the K value is supposed to be less than 1. So it's just a reverse. A step-down voltage transformer automatically works as step-up current. Automatically. See, the voltage gets down, so the current is up. So that's what is required sometimes. You want a balance. Right, so we thought that it's a step down basically, but what came out actually it's a step up current. Voltage goes down, the current goes up. And similarly, if you are designing a step down current, why do we require that step down current? Step up current we understood. In our household, we require a high value of the current. And therefore, we must lower the voltage. And so we will get a higher current. Got it? Step down current transformer. This is when it is a step of voltage. That means now we will have IS less than IP, correct? And we have NS more than NP, and the value for K is more than 1. The transformer, once again, obeys energy conservation. There is no violation. There is no violation of conservation of energy. Why so? Why there is supposed to be no violation? The reason is very simple, my friends. The reason is because when we're talking about the V into I product or E into I product, that is behaving constant. Why? As E is proportional to 1 upon I over here, because it's about the power equal to V into I, and we're telling the power is 100% efficient because if eta equal to 1 in that case. So E is proportional to 1 upon I. So what is happening? If the voltage increases, so we might think that it's a violation. We are delivering a perpetual engine. We are generating so much high voltage. How come it is possible? It is possible at the expense of the current, because the current is coming down, and so the voltage is rising. So there is no violation. Because the product is anyway remaining same, so the energy is still conserved. The power is still conserved. The overall energy flowing per second is conserved. So there is no violation of this. So high efficiency and no violation is an excellent concept. So we have understood that how does a transformer is designed, and what as per your workings you can use a step down or a step up transformer. So uses of it is used as a step down voltage device for charging smartphones, laptops, USB devices. Right? It is used for voltage regulations across TV, air conditioners, etc., refrigerators. So very much what we use daily. We use daily. Third, it is for power stabilization. More, it can be used as a step-up current. The step-up current transformer. Where do we require step-up current? Where do we want exactly high currents? Very high currents. Very high means very high, not of the tune of the 1 ampere, 2 amperes, very high currents. So what is the use? For weldings. For weldings, for the welding, and for furnaces. Right up, and more use, you can use it for production of the X-rays. And the sixth, it is for highly efficient power transmission. That means whenever you're transmitting the power over the long distances, that is a power transmission. Across long distances. So what is an idea? See, what is an idea is when you're transferring it over the long distance, so you'll be requiring a transmission wire. So if you're using this as a transmission wire, so what is happening? What is happening if you're using the transmission wire? Now, there is a long length of it. See, if the power plant and your house are 10 kilometer apart, 20 kilometer apart, 30 kilometer apart, then you'll be using 30 kilometer long wire, 20 kilometer long wire. So these are long wires used for transmission. And long wires comes with a problem. That's a resistance. That's a length is very large. So resistance is very large. So the power, that is I square R, goes into huge losses. So it incurs huge power losses. So therefore, the output received is very low because there is most of the energy is getting lost in the transmission. So the output received is very low. So you will complain of low voltage coming to your house, which cannot keep up with your devices. Your devices may not meet up to the specification and they get damaged because you are either using underlighting sometimes, or sometimes you get a spurge, you know that. Sometimes you get over voltage. These days we don't get over voltages because there are highly efficient devices in place. So we don't get a surge of the voltage that way. So, but low voltage can be there if there is no supposed to be some mechanism in place which can prevent the power losses. So transformer is kind of providing a mechanism through which we can prevent the huge power losses during the transmission. The question is how it is able to do so, because the resistance is so high. So there's only way, one way, that is to reduce the current. That's I square. So if I becomes, let's say, 1 upon 1000, so square that, that is 1 upon 10 power 6. And so the power losses go gone. So it becomes negligible power losses. So you need to devise a mechanism in which you can step down the current. So you know that the transformer can do that. You've just seen the 4 ways of the uses of the transformer: a step up voltage, a step down voltage, a step up current, a step down current, as you require. So you want the current to step down, which basically means what the voltage should be very high. So at the input, this is the input of the transmission line. This was an NC over here, correct? And we have this as a transformer. So what is this? This is a step-up voltage transformer. So step-up voltage transformer. So what happens if the voltage over here was supposed to be, let's say, V0, over here it becomes V. And V is N times of V0, where N over here is extremely large. That's basically the transformation ratio. So the N is very large. That means the value for the V is stepped up. And then what happened? These are the transmission lines, two-way transmission lines. Right? So that's a two-way transmission lines, which ensures a closed circuit. One-sided, it will be an open circuit. So two-way transmission lines. So there will be the resistance here also in this line. And there is supposed to be the resistance here also in this particular line. And then they reach their destination. So we can mention that this is supposed to be the transmitting end. And this is supposed to be the receiving end. And so it reaches over here. And what do we design now? What do we design now? See this? This is a transformer. And what we have designed? What we have designed? We have designed this. So what is this? It's a step down. So it is supposed to be now a step down transformer at the receiving end. So the voltage which was over here, let's say V dash, which is the output, is going to step down, So over here, the final voltage, that is a output voltage over here, is supposed to be lower because we have stepped it down, and it is, maybe it comes 440 volt or 220 volt. See, there is a three-phase behavior also. From first of all, you step up at the input end, and then it comes to a locality. The locality transformer reduces it to 440 volt, and when it comes to your mains, your individual house main, it reduces to 220 volt. So there will be two transformers in between, and there can be many in between also. Well, let's say the power plant is very far away, so in between also we'll put up a transformer for a district, and from there it is going to go to a locality, and from locality to your house, and then into your house, then into your charger, and charger also have a transformer, or to a refrigerator. So in between refrigerator also will have a transformer. So many transformers are going to be used. Wherever you require a change in the character, sometimes you require high current, low current, high voltage, low voltage, high voltage for preventing the power losses as now. So what happens at the input? So at the input, we have the voltage stepped up. So V stepped up. So that means the V is very high. So the input power, that's energy conservation. Do you remember? I told you energy conservation. That is V into I. This is at the input. This is at the input end. So V is very high. So therefore the current, which is equal to P upon V, but V is very high. So the current becomes extremely low. So that's what the use of the stepping up the voltages. So therefore the current used, this is the input current. So current used in the transmission is very low. And therefore the power losses across the transmission wire, that was I square into R. So I square becomes so low. So therefore the power losses are kept to minimum. And this is how we minimize the power losses during the transmission. And then at the receiving end, what do? So power losses are anyway less. And the receiving end, what do? We step down the voltage. So we step down the voltage. As the voltage goes down, so the power basically exhibits, because of power losses, the power variation has been lesser. Reason because the power losses are kept to the minimum. In that case, the power is almost delivered with a high efficiency. So the power, let's say, that assumes constant. So the V goes down now. So the current rises up, and you get a high current in your circuit for your device. And you can bifurcate it into the parallel circuits now, right, across your house. That so all of the current does not go to one room, and you're a single device. So, but you require the main current to be higher. So we get main current to be higher like this. So that's your description, and everywhere we have used the language, the high efficiency. So how do we get a high efficiency? So how do we ensure high efficiency? So that is only one way. That is by reducing the losses. That is by analyzing, reducing the losses. So let's check which kind of losses are there. So first kind of the loss is known as a copper loss. And what is a copper loss? We say, see, across the turns of the coil, there is heat generated as I square RT, which generates power losses. Correct. So what do? We do a correction. And how do we prevent these losses? It's simple. It's very simple. That is by using thick copper wires. So thick copper wires means the resistance goes down, the resistivity goes down, and because of which the power losses are prevented. So that's how we control the first loss, the copper loss. The second loss is the eddy losses. Now we know there will be the eddy current set up in the core of the transformer. So due to the varying magnetic flux, eddy currents are set up across the core of the transformer. So what do? That's the reason we have constructed it like a group of sheets. So how do we reduce it? That can be reduced. This is how we reduced it, the copper losses. So it can be reduced by using laminated core. Right, so which basically breaks the continuity of the eddy currents as we have read in detail in the article of the EMI. So by using the laminated core. So why do we use a laminated core? That is to reduce the eddy currents. That's the second loss. The third loss is supposed to be the flux losses. The flux which is generated across the coil. We know that. We have read in the solenoid that the field at the center is mu naught Ni, but at the ends it is mu naught Ni by 2 because there is a flux losses. So 50% of the flux will be lost and the coupling will go awry and the efficiency is going to get into 50%. So what do? Right. So what happens? That there is a string of the field. The string of the magnetic field, because they run everywhere, because of the coil, they run everywhere. They tend to form the closed loops. The string of the magnetic field lines causes the flux losses, which affect the coupling. So how do we reduce it? So the reduction is just around the corner by using the soft iron core. So what does that soft iron core does? We're using the soft iron core. The soft iron core is highly permeable. That means its permeability, the magnetic permeability is very high. It's very high. So therefore, all the flux is passed on from the primary to the secondary via the core. Core means that's a ferromagnetic core, because the soft iron is a ferromagnet. Now, using a ferromagnetic core, comes the fourth loss, which is known as a hysteresis loss. One event leads to another. Hysteresis is supposed to be a cycle of magnetization and demagnetization. This is how loop is there for hysteresis. That is magnetization by the magnetizing field. So due to the varying AC input, of course AC is always varying, there is continuous magnetization and the demagnetization of the core, which causes energy losses. Of course, when it will be continuous behavior, once it is getting magnetized and demagnetized, so there will be energy losses. And that energy loss is directly proportional to the area of this loop. And this loop is known as a hysteresis loop. So area of this hysteresis loop. So which means, how do you reduce this? So select the ferromagnetic material which has lesser loss, which has a lesser loss. Hence, we use soft iron core, because a hard iron core has a large area and therefore it has large losses. So we cannot afford those losses. So we use a soft iron core. So if you get a question, why do we use a soft iron laminated core? So soft iron because of reducing the flux losses and hysteresis losses, and laminated because to prevent the eddy losses. Are you getting the point, right? So we have the thick copper wires wounded on the soft iron laminated core. Now what's the answer? The thick copper wires to reduce the copper losses, the soft iron core to reduce the flux loss and the hysteresis loss, correct? And the laminated core for reducing the eddy losses. So that means you have taken care of all the losses, but still there is another loss, that's a final loss which creeps in, and that is known as the humming loss. Humming, that sound that you get in the fans and all, right? Humming loss. So why does a humming loss comes? That is because of the AC behavior, because alternating current which passes through the structure, it enforces the AC fed to the core of the transformer. It gets to the core of the transformer also. Causes the contraction and elongation of the core. You remember we did a question that we have a current carrying wire and is kept in a magnetic field so it may expand. And we calculated the tension in that wire and amount of the radius it expands. And if you pass on the current in the reverse direction, what happens? It can contract, right? Expansion and the contraction of the loop. So exactly what happens here. When you are feeding the current, so associated magnetic field is also reversing in direction. And because of which what happens, there is supposed to be the continuous contraction and elongation of the core. So the core is set into vibration. Therefore, the core is set into vibration. This is known as magnetostriction. So what is magnetostriction? Magnetostriction is basically an idea that is supposed to be the vibrations in the core because of the shape changes. What is this? Because of the shape changes. And what are the shape change? Because of the contraction and the elongation of the core, which generates accessories connected. So a screw is connected to a core. Sometimes it gets loose, sometimes it gets tight. So what happens? It will generate some noises because it is not completely fitting. As if the two vessels are not properly kept and they're just kept loose. So what will happen if you move it? So they will keep on generating noises because they're not exactly screwed properly or coupled properly. And that's what exactly happened with the accessories and the casing in which the generators are kept. So hence, the accessories and the casing develops noise, which is known as humming. So how we can reduce that? That is by keeping the casing slightly away, the accessories to be properly nutted or riveted. Instead of using the screws, we use rivets, and such that they don't make any noises. So we can reduce it. So reduce it by proper encasing, proper placements, You just cannot keep transformer like that. So you need a proper installation. So proper placement and installation, and fitted actual accessories. You cannot be using the spare parts like that, anything. It should be perfect over there. So the humming noise will not be there. Same goes with the actually company generated parts of your auto. Auto means your car, right? So car or bike, whatever it is. And if you don't buy the proper accessories for that, so it may generate humming noises once again, because they don't fit into the compatibility of your working devices. So you should be using the genuine parts always, because they fit the accessory part, and this will not, because most of your devices work upon AC. So if this idea occurs in the case of the transformer, it also occurs in other devices also, and therefore you get unwanted noises. And it's a very important part of the communication part. That's the noises. And in the communication part, which is of course this year not in your syllabus, so we read that in the communication chapter, to reduce that noises, we need to feed high ACs. If you feed high AC, then those humming sounds go off. Right, so that's during the communication part. This is in the core part of it. This is not a communication part. This is the core part of the transformer, where we are restricting it by proper placements, installations, and all. During the communication, while the waves are moving, and during that particular time, if you keep the input frequency higher, so the humming loss goes off. Okay, because that vibrations will not be heard by you, or not listened by you. It will go off the ranges, and therefore you will not feel that particular noises. It's what you hear is the noise. If you can't hear anything, that's not the noise. So that is supposed to be your complete transformer article, and one of the most efficient devices. So the practical efficiency of the transformer is supposed to be around 90%, and can be increased to 99%. And the most efficient get 99.99%. So we keep 0.01% for some kind of the losses. And if we have small transformers, so the encasing is not an issue. Encasing is not an issue. You can use them just like that. So can be used without encasings. But if you have the large transformers, very large transformer, you get in the factories where the whole area is supposed to be run like a private area, where you require so much of the power requirement for everything, like the large factories setups, like we can say like a Microsoft office completely, or an Infosys office in the Mysore, where we have around 50,000 employees working in a single campus. So you'll be requiring dedicated supplies over there. So we'll put up a large transformer over there, and the large transformer is supposed to be properly encased in all tanks, because they produce heat, right, to minimize the heating losses. So I have dealt with every nook and corner. So one thing has to be developed finally. When we talked about that, we are not going to generate the input resistance. We said that we are not going to generate the input resistance. But because of the phase variation in the output, there is an input resistance automatically generated. How come? Let's see. See, when we write the output resistance, that will be the output voltage upon output current, correct? Correct. Now we have K, transformation ratio, which was basically nothing but NS upon NP, as equal to ES upon EP, correct? So I can write ES as equal to K into EP, correct? And this is equal to IP upon IS. So I can write IS is equal to IP upon K. So instead of the ES, I'm writing as K into EP. And instead of IS, I'm writing IP upon K. So this becomes EP upon IP and into K square, where K is the transformation ratio. Now, what is EP upon IP? So the EP upon IP, that becomes what? The input resistance, which we did not apply, but it came on by itself because of the behavior of the output. We are checking the theory from the output. We are not checking from the input. Input we did not apply. We use the thick copper wires over there. We did not apply. But what is happening? It is generating an input resistance by itself, a virtual resistance. And how much is that? That is is equal to R naught upon K square. That is equal to R naught into K is what? Ns upon Np. That is Np upon Ns whole square. That is supposed to be the virtual resistance which is induced in the primary because of the behavior of the secondary. Right? So whatever load you are applying over there, accordingly, you are going to get that particular result. Step number of turns in the primary and the number of turns in the secondary, and whatever load you are applied over there, according to that, the input resistance is going to behave. So if you are using a step up transformer, so Ns is very high, so Ns upon Np will be still very high. So R naught upon that value will come out to be very lesser, so the input resistance will be very less. So with this article, I'm going to wind up the article of the transformer. That's a complete theory, complete use, definition, principle behind it, and the working, the construction, the types of it, the practical use of it, the efficiency of it, the equations behind it. Right? So real part and the virtual part of it. Everything of this has been discussed. So I'm just closing down this transformer article. Thank you. Okay, bye.